Okay, so our next speaker is Gleb Pogudin from Linz. He also has changed his title slightly. And he's been
no, I haven't.
It's not the one that I have written in my program. New effective differential Nullstellensatz.
Okay. First of all, I want also to thank the organizers bringing all us together in order that we could enjoy this wonderful math during previous days and today already. What I'm going to talk about is a joint work with Alexey Ovchinnikov and Theo Wong from New York and from Linz, respectively. Effective differential Nullstellensatz is just a sort of important theoretical bound in differential algebra, but I will speak about it mostly in the context of solving system of algebraic differential equations. So, I'll begin with incredibly simple examples. Okay, let's look on the first example. I think it's evident that this system is unsolvable. Moreover, it is unsolvable in some more strict sense. It is unsolvable even you have no any idea how are f and f prime related. You don't even know that one of them was obtained from another by differentiation. You just can think that f is like u, f prime is v, and obtained algebraic system is inconsistent. So you have no chance to solve this differential system. The second example is essentially the same, but it is solvable in this algebraic sense. So if you forgot the relationship between f and f prime, then this system becomes solvable. But of course, when you differentiate the second equation, you'll obtain the first system, which is, let's say, very unsolvable. As we see, there are unsolvable differential systems of just two kinds. One of them are unsolvable even as polynomial systems, and others are just unsolvable. And in the first case, when the system is unsolvable as a polynomial system, it can be just checked algorithmically because, okay, of course, we have many different tools to deal with polynomial systems. So the general statement is formulated in terms of differential algebra. Let me remind it briefly. So we have differential field is a field with one derivation. I will not speak about partial case almost. A right algebraic object for system of algebraic differential equations is the algebra of differential polynomials. So I have variables x1, xn, which I consider as unknown functions, and I consider all their derivatives as separate algebraically independent variables. And essentially, when I have a system of algebraic differential equations, it is a system of differential polynomials which are equal to 0. So this is differential algebraic framework. And as in an algebraic case, instead of considering just system of equations, you can generate the ideal and consider it. It's more invariant object. And we'll have three different types of ideals today. First of all is just differential ideal generated by given polynomials. The second one is radical of this ideal, which corresponds more or less to solution set. And the third one is not differential ideal. It's just algebraic ideal. It's ideal generated by differential polynomials and the derivatives up to order n, but actually this is up to order n and n also, including n. The reason of introducing the third type of ideals is that first two are quite hard to deal with. So we have this chain of inclusions, and computationally we work always with the third type. And in the sense of solvability, we have differential Nullstellensatz, which says actually that if you have a system of differential polynomials which has no solution in any differential extension, then one lies in this differential ideal, and it also implies that one lies in such an ideal for some n. And more or less the same holds for just strong form of Nullstellensatz, that if you want to check if given differential polynomial vanishes for all solutions of your equation, of your system of equations, then again it happens if and only if polynomial lies in the radical of the differential ideal, and again for every polynomial it's sufficient to have some truncated differential ideal. And the problem is to determine with this number n, because if they know n, our problem is immediately reduced to just polynomial computations. Okay, what's known for today? The first bound was obtained by Golubitsky, Kondratьева, Ovchinnikov, and Zanto. It was for partial differential equations, so it was more complicated problem, and it used more or less Rosenfeld-Grobner algorithm as a ground argument, and it's somehow connected to what Amar and Richard told on Friday, and that's why you see here an Ackermann function also. So this bound indicates that there is a bound, but it's not very visible. And the second two bounds are based on the prolongation projection approach, which goes back to more or less Cartan. I will give a brief description in several slides. And again, this looks much better. And the first work was about ODEs with constant coefficients, and then it was generalized to PDEs with coefficients in an arbitrary partial differential field. But the problem is that, first of all, these bounds were not concrete. They had big O, actually. Here I write C. Here I also have almost the same C. And if you look closely, you'll see that this constant C is at least 3. So when you substitute some numbers, here you will now get numbers which you want really to compute with. So they will be like some numbers, but too big to compute, too big to write down. Okay, and here's our bound. First of all, I want to give some definitions because it's more flexible. Okay, what do we have? Actually, we have a part of ring of differential polynomials. So for each variable, we bound its order. So we have vector of orders. And we have polynomial systems. We have D0, it's minimal degree, D1 is maximal degree. And we denote by M dimension of the ideal, which is generated by these polynomials as just an ideal in this RH. So more equations you have, less M is. And of course, for inconsistent systems, you normally have not one or not two equations. Okay, actually not one, and quite rare you have two. And again, one belongs to the differential ideal if and only if. One belongs to this truncated ideal if n is bounded by the following formula. So what's good about it? Okay, I will talk about numbers a bit later. In the sense of asymptotical complexity, first of all, it's much longer than previous one, but it's much better. because if you fix M, fix a dimension, it depends on A and H single exponential. In this respect, it behaves more or less like Grobner basis bound, because in general, computations of Grobner basis are double exponential, but if you fix a dimension, then it becomes single exponential. Yeah, but okay, it's still double exponential in the dimension. Another thing is that it allows you to take into account, first of all, different orders, different variables. It actually makes sense in real life. And it behaves better if you have at least one polynomial of small degree. For example, if you have linear polynomial, then this factor will disappear. And normally you have at least one linear polynomial in some real systems. Okay, it's the first new thing. Actually, this is the second. Several slides ago, I mentioned that there is weak Nullstellensatz, which determines if 1 belongs to the ideal, and there is strong Nullstellensatz, because you sometimes want to understand if this system of equations imply something. And of course, you can reduce strong Nullstellensatz to weak Nullstellensatz using famous Rabinovich trick. But if you use this trick, then the degree of the polynomial which you want to test will enter to the bound. Normally you don't want it, especially if you want to avoid it. In this case, it turns out that you can avoid it, so we can prove the same statement. This is literally the same bound as on the previous slide, for testing membership for some polynomial in Rh. And it does not depend on the degree. This type of Nullstellensatz didn't occur in the previous papers, which I mentioned. And okay, finally, let's look at numbers. They can be written down, and with many of these numbers, I actually want to compute. So 52 variables. It's okay. That's what happens. And also I want to mention that you have quite a lot of flexibility. So if you see something good about your system, like you have small order with respect to one of the variables, you can use it and it will improve the bound a lot. Also, if you had a good memory and good computational skills, you can find some sort of deception, because these numbers are not the numbers which you will obtain plugging in this n and h to the bound I showed you. That's not because I'm a liar, but that's actually because in our proof we have more tight bound, but it is some kind of sum. So the actual bound is 2 or 3 times better than bound I showed you in the previous slide. And that's it. Okay, that's actually what about result. And how do we get it? First of all, I want to outline a general scheme of prolongation projection approach. What happens? At each step, you have some ideal in this truncated ring of differential polynomials. Let me remind that Rh is the ring which is generated by some differential variables and their derivative up to some order. So, and you can differentiate all elements of the ideal. You will have elements of bigger ring and then intersect it back. Actually, there are 2 possibilities. First one is that you will get back your ideal, and the second one is you will get some new polynomials. So you will get some polynomials of higher order, then there are some contractions, subtractions, and so on, and you get back polynomials in Rh. And actually, what the first lemma says that if the ideal generates an inconsistent system, you will drop dimension at each step. You will get new polynomials at each step of prolongation projection. Modified lemma says that what do we want? We want to know, finally, all polynomials of the radical ideal generated by I, which lie in Rh. And there are two possibilities. Either you already have all them, or the dimension will drop. So this gave us some inductive procedure. Either we already arrived, or we can perform prolongation projection and the dimension will drop. So we cannot do prolongation projection too many times before we actually arrive. Okay, how can we do it? Okay, really, we need to have some sort of representation of the ideal we work with. What do we do with ideal? This is example. Yeah, sorry. I have an example. In this example, you have some 3 polynomials, and then differentiate them, you will get 1 u. So in order, you cannot get it just performing algebraic operations with them. You need to differentiate them, perform some algebraic operations, and then you will get new polynomial in your initial ring. And the dimension drops from 1 to 0. And actually, it is 0. The system is consistent. Okay. What about the representation? What we do with the ideal? We differentiate it and we intersect it. Okay, good possible choice is the Grobner basis. Because you know that, of course, if you want to differentiate the ideal, you can just differentiate its generators. Grobner basis is a set of generators. And of course, you can project using Grobner basis. You just should take lexicographical order or some other eliminating order. The problem is that Grobner bases have not very good complexity, especially when you want to represent not the ideal itself, but its radical. And it is not because we don't know something about Grobner basis. There is some negative counterexample which shows us that just if you have some polynomials of relatively small degree, which have some irreducible algebraic variety as 0 set, then every set of generators of the radical ideal will have at least one generator of double exponential degree. So you can prove any refined result about Grobner basis and then use it. So if you have Grobner basis, you have double exponential complexity on each step of prolongation projection. What can we do instead of that? We can make use of triangular sets. This is some also classical thing actually for differential algebra, but okay, we use it in a very different way. So what is the triangular set? The triangular set is just a set such that leaders of all polynomials are different. So you have some order on the variables, not on monomials like in Grobner basis, just in variables. And you compare leaders, and okay, leaders are different, and you can order your polynomials. And there is a classical way to represent an ideal using triangular set, is call an ideal with respect to product of leading coefficients. So polynomials which lie in this ideal are exactly the polynomials which has 0 pseudo remainder with respect to this set. And it turns to, it's quite easy to use them. First of all, we have a good theoretical complexity result, which helps us to bound the degrees of the triangular set as degree of the variety times 2. the problem is with differentiation, because when you have set of generators, you differentiate them, and okay, everything is good. Here you don't have the set of different generators, but it turns out that if you choose the triangular set in some tricky way, you can actually take a derivative of one of them. So it will have the same degree bound as we have in the first lemma. So the first statement is about all triangular sets. If you want to get the second one, which says what happens when you do prolongation projection, you need to choose triangular set carefully. And in this situation, you actually square the degree of the variety at each step, and the right examples, then it really squares. So you cannot perform one step asymptotically better. But there is a problem, because there is word prime everywhere. So actually, not every every ideal can be represented as triangular set. By the way, you might see the poster about computational part of all this stuff. And then the algorithm actually produces several triangular sets, because for each prime component. So we can solve problem for prime ideals, and then we should somehow glue it all together. And it's done by the following just differential algebraic lemma. So actually you can relate different derivatives of ideals and derivatives of their intersection in such a way. And actually you can even determine this number S, but I won't speak about now. So that's actually all what I wanted to say about the proof. I have some time, let me outline what happened. What really happened? Okay, we finally have bound with numbers which are computationally feasible and imaginable. We have the same bound for strong Nullstellensatz, so for some quite normal systems, you can test membership for polynomials of very high degree. And the third thing I want to emphasize is that it is some kind of success story when you replace Jobna basis with something other, in this situation triangular sets, and things became better. And I think it actually not the only case. Maybe if you have problems with Jobna basis, think about triangular sets, they do the job. So that's all, thank you.
Questions?
I have a question.
Mm-hmm.
So I really like the modified basic lemma, and I guess I guess if there exists some analogous result for several derivations, so
yes.
I think you just need like one step, and I guess if it is because it is the ordinary case.
Yes, you are right, and actually all this can be carried out for several derivations, but you will not get that good numbers. That's why we did not that. But for several derivations, you will not have. Yes, you will have one here. Yes, you will have one here. Yes, you will.
Yeah.
But you need to prepare your ideal before that. So in several derivations, you take some number of derivatives, and after that, at each step, you differentiate only one time. You can look it in the paper of.
It is written in the paper.
In this paper. This paper, it deals with PDEs, and they do prolongation projection, and they have projection lemma for several variables.
Oh, wonderful, yeah.
Yeah, look there. And two of authors are here.
Okay.
So this, this method is using this prolongation projection method, so it's still kind of inductive or recursive. Are there reasons to think that this is the best you can do, or might you be able to use something like Belbin's and Yamini's methods bring the exponent down, bring it from double to single exponential.
Okay, we don't have any examples which will show that bound is really sharp. But, okay, and being honestly, we don't have many examples. For one derivation, there is a standard example in actually the paper I just pointed at, and it has fixed dimension, and in number of variables, it really behaves single exponential. So in this respect, maybe it's the best. But in number of derivatives, it behaves a bit different. So it might be done better. Actually, I personally believe that this constant 2 can be raised, but it might be very hard. Or maybe really you can just invent any approach because, okay, maybe the inductive procedure is not the best choice. But we have some reasons to think that at least with respect to n, it's already quite sharp.
Okay, thank you very much. The next talk is at 3:10.